Welcome to The Explainer. Today, we're diving into a paper that absolutely changed the game for building huge AI models. We're talking about a way to make them bigger and faster, but also, believe it or not, way more efficient.
So, let's get right into it. The story of the switch transformer really starts with this massive problem in AI. There was this frantic arms race to just build bigger and bigger models, and it was getting completely out of hand, totally unsustainable. You see, it all kicked off with something called scaling laws. These are basically predictable rules that showed, hey, if you just scale up a model's size, the data you feed it, and the computer power you throw at it, its performance just keeps getting better.
One of the key findings here was that it's actually way more efficient to train a gigantic model for a short amount of time than a smaller model for a really long time. So naturally, this set off a gold rush to build these enormous models, but the way they were built, using what's called a dense architecture, was just incredibly wasteful.
With a dense model, every single parameter, every single artificial neuron gets activated for every single piece of information it sees. It's like forcing a genius to use their entire brain for every single thought, no matter how simple. So researchers realized, there has to be a better way, a more selective, specialized approach. And this is what led them back to an old idea from the 1990s, but supercharged for the modern day: the mixture of experts, or MO.
The whole concept is it's beautifully simple. Instead of one giant monolithic network, you have a bunch of smaller, specialized expert networks. And here's the magic. You also have a router that looks at the incoming data, like a sentence, and intelligently figures out which one or two experts are the best fit for that job. It's kind of like a smart receptionist who sends your call to the exact right department instead of making the whole company listen in.
Now, the mixture of experts idea was a fantastic start, but it was still kind of a headache to train and could be pretty unstable. The real breakthrough, the moment everything clicked, came from a radical simplification of this idea, and that gave us the switch transformer.
The core innovation here was honestly just stunningly simple. The switch transformer took that mixture of experts idea and made one tiny, crucial change. Instead of routing a task to a few experts, it sends it to only the single best one. That's it. This one little tweak sounds minor, but it completely slashed the communication costs and simplified the whole algorithm.
And the result of that simplification? Well, look at this. A 7-time speed up during pre-training compared to a dense model with the same computational cost. I mean, that kind of jump is almost unheard of in deep learning. It was a massive signal that they were onto something huge.
But look, making these massive trillion-parameter models actually work took some real engineering genius. The researchers came up with 3 key tricks to tame the beast. First, they used higher precision math, but only for the router. Second, they initialized the model's weights with much smaller values than normal. And third, they used a technique called dropout, which helps prevent the model from just memorizing things, but they applied it only to the expert layers. Just brilliant stuff.
Okay, but the switch transformer didn't just make models faster. This is where the story gets really interesting. It led to this profound discovery about the very nature of AI, and it forced everyone to ask, what's the real difference between knowing a fact and actually reasoning with it? This led to this absolutely fascinating hypothesis, summed up perfectly here by one of the researchers. A model's parameters, all those connections, are like its library. That's where it stores all its knowledge. But its computational power, its flops, that's what determines its intelligence, its ability to reason with what it knows. So, to test this idea, they set up this brilliant experiment. They put a powerful 13 billion parameter dense model up against 2 sparse models. And one of them, this Switch-C model, was an absolute monster with 1.6 trillion parameters. But, and this is the critical part, it had only about 1/10 of the computational power for each token it processed. So what happened? Well, on benchmarks like Superglue, which are all about complex logical reasoning, the dense model with its huge compute budget came out on top. It seemed like intelligence really did depend on that raw computational power. But then they switched to a totally different kind of test, Trivia QA, which is all about factual recall. just raw knowledge. And here, the roles completely flipped. The sparse models, with their vast library of parameters, were just way, way better. They were like walking encyclopedias. So here's the takeaway. That massive 1.6 trillion parameter model, even with its tiny compute budget, was an absolute superstar on that knowledge test. It completely confirmed the hypothesis. You can literally design an AI to be better at reasoning or better at knowing things just by changing the ratio of its compute to its parameters. Mind-blowing. So where do we go from here? I mean, this breakthrough wasn't just some academic exercise. It's already unlocking entirely new ways to build and actually use AI in the real world. One of the coolest applications is a process called distillation. You can train one of these giant trillion parameter sparse models, and then basically distill or compress all of its knowledge into a much smaller, more practical, dense model. And what's wild is you can shrink the model by up to 99% and still hold on to about 30% of the performance gains you got from sparsity in the first place. And this technique is now supercharging everything. For multilingual models, you can have different experts specialize in different languages, leading to these huge speedups. In computer vision, models can learn to just ignore the boring parts of an image like a big blue sky and focus their computing power only on what matters. This is really the beginning of a truly adaptive AI. And all of this leaves us with a final, really provocative thought. The switch transformer didn't just give us a faster way to train models, it gave us a whole new set of dials to tune the very nature of intelligence itself. So the question we're left with isn't just about how to make AI smarter, but what kind of smart we actually want it to be. Thanks for joining me on The Explainer.